In this lecture, we want to take a look at reference variables and the way that they access the computer's memory. The reason for this is that very often new programmers discover that variables don't behave quite the way they expected, and they're unsure why they don't behave that way and exactly what's going on. So we want to take a look at these variables and see how they operate. The other motivating factor here is the fact that null pointer exceptions are the bane of every student's existence in CS 310. When null pointer exceptions happen, and they will, we want to know why they happen and what's going on. If you understand the behavior and understand why you're getting a null pointer exception, it becomes much easier to find and fix the problem. The big picture, the big idea here is there are two general classes of variables. And this is true for all programming languages, not just Java. We can have variables that hold values, or we can have variables that hold addresses. We can have scalars that hold values, and these are primitive types, such as an int, or we can have references, which are addresses. So either of these is possible. It is the reference variables that seem to cause the most trouble, so we want to take a close look at those and try to get a deeper understanding of how these are stored in the computer and what's going on. In Java, the two types of variables can be characterized this way. The first type is primitives: byte, short, int, long, float, double, boolean, and character data. So primitive variables hold data or values. Int x equals 2. The memory location identified by this variable x holds the value 2. Objects. Objects are everything except the primitive types. Also, the Java language has object versions of the primitive types. So we have, for instance, the object byte, which is capital B, the object short, the object integer, and these correspond to the primitive variables. Object variables hold addresses. They hold the address of the actual data, but not the data itself. For instance, when we have the declaration person P equals new person, person is not an object, but a pointer to one. So we allocate memory for P, and at P we store an address. In another section of memory, the heap, lives the actual person object. So P has the address of that actual person object. Memory for variables can be allocated either on the stack or on the heap. This is not quite as important as understanding the behavior of these reference variables, but it is important, so we want to talk about this for a moment. Primitive and object local variables. By local variables, I mean variables that are declared inside of a method. These are allocated on the stack. Class-level variables are allocated on the heap as part of the class. Object variables can be allocated either on the stack or on the heap, but the actual objects, the instantiations, must always be allocated on the heap itself. So the idea here is simple, but the implication is anything but simple. So I want to switch to the Sketchpad for a minute and look more closely at what's going on here. So we have a system stack. Now the system stack goes with every process or program. Each program or process has a system stack, and this is not the same thing as the data structure stack that the programmer might use in a program. Rather, this is a chunk of memory that's used for allocating variables and also for facilitating functions, method calls. So this is the stack, and this is the heap. So we have activation records or stack frames here When you invoke a method, certain things get pushed onto the stack. Parameters to the subroutine. Also the return address so that the flow control can return you back to the calling module. Local storage and also saving state. So what we're primarily concerned with is local storage. And so if we say something like person P equals new person. Now I've made two statements out of this. It's very common to do it as one, and it doesn't really matter, but I want to separate the two steps so that we can see what's going on at a finer level. So we'll assume that this declaration is in a subroutine or a method. So on the stack, we get our variable P. It's allocated here. Now, object variables are always initialized to null, and then they may be changed once you've allocated the actual instance. So we go down to the second line and we have P equals new person. The keyword new causes memory to be allocated on the heap for this actual person instance. We don't know how many bytes are involved here. It depends on the size of a person. It's not really important, the actual size. Now the starting address of this chunk of memory, the first byte of this chunk, has an address. We don't really know what it is. We'll call it A just for simplicity. But this A is returned in this assignment statement. So new person creates this instance on the heap, and the return value that's assigned to P is the address where it actually lives on the heap. So now the null is overwritten, and we have the actual address of where that object is on the heap. Class level variables are here. So we might, for instance, have something like private int, and something about a person that's an integer. I don't know what. Let's say zip code. It'd probably be a string, not an int, but it will do. All right, so you have here a chunk for the zip code. And this is a scalar, and so the value is stored right here. But you might also have something that's an object, string name. So what we have here is the name of the person, and it goes there, and it isn't actually stored there. It's an object, so it's allocated on the heap. So we get the address of that, and here, where we expect the name, is B. So these chains can be quite convoluted at times, but the important point to remember, the essential idea here, is that when you have an object, there are two parts. With an object, there are two parts. You have the actual variable, person P, and then you have the instance that P points to in another section of memory on the heap. Here we have an actual person instance. And it's got some address. We'll make something up here. 421C. So this is a hexadecimal address, and this is the address of this very first byte of this person instance. And when we say P equals new person, this causes the allocation to occur on the heap, and the return value is this address. So here we have 3116421C. Then when we dereference this variable, P dot set name, for instance, that says, go to P and read the address that's there. And the dot operator is a dereference. Go to the address that P points to and set the name. Go to the address that P points to and set the name. So object variables always have two distinct parts. The reference, which may be allocated on the stack, or it could be on the heap. That is, it will be on the stack if it's declared inside of a method. It will be on the heap if it's a class level variable. The object instances are always allocated on the heap. So as an example, we have public void myMethod. Int x allocated on the stack. Person P also allocated on the stack. P equal new person. The actual instance is allocated on the heap. So there are two pieces to this person P. Some common mistakes. This first one, person P. P dot set name John Smith. That won't work. Well, why won't it work? And then we have an if test. If P dot get name dot equals John Smith. No, this doesn't work either. What does work? Person P equals new person. The keyword new is used, and that's fine. Person P equals Q. And then I intended to put Q dot set name, but I've got P dot set name. But the point is they're both the same thing. So I'm going to switch to the sketchpad for a moment and look at this example and see what's going on. So I say person P. Then on the stack we have P. And there's no instantiation, so the initial value is set, it's null. Now if I call P.setName, what happens? This says go to P and read the address you find there, go to that address and invoke the setName method on this address. So we go to P and it's null. There is no null.setName. Therefore this throws a null pointer exception and the program will crash. Similar to the if test, if we do an if test, if P.getName dot equals John. This will also crash. Both of these methods would cause a crash. But once it happens with the first one, then you're out of there. Go to P and invoke the setName method. Go to the address in P and invoke the setName method. I think you can see this isn't going to work. You can't call getName on null. Alright, so the second part of this, we have person P equals new person. So on the stack we have an allocation for P, just as we did before. What's different this time is we have the keyword new, which causes memory to be allocated on the heap. So we have a person here. This is the actual instance. The starting byte of this chunk of memory has an address. Let's call it A just to make it easy. So the null is overwritten. P now has an address in it that exists on the heap. P points to this object that's sitting on the heap. Now we have another twist to this. Suppose I say person Q equals P. What happens now? I create on the stack another variable, a Q. And its assignment statement, it gets the address of the single person instance on the heap. So both P and Q point to the same object. Thus there's one object and two references to it. Both of these point to the same object. So I can do this, P dot set name Henry, or I can do Q dot set name Henry, and both of these statements will do precisely the same thing. There's no difference at all. Both of these say go to this address, go to A, and set the name here in the actual instance on the heap. The next one I want to look at here is using a data structure stack, and this is something you would use in your own program. This is not the system stack, but rather the data structure stack. So we have person P equals new person, we have the variable on the stack, and we have the actual instance of person on the heap. Now we have an array of strings, and we have a loop where we go through in a for loop and we push each of these onto the stack. So we push John, Sam, Sally, Robert. We have p.setName array I. So we have p.setName John, then Sam, then Sally, then Robert, and we push that onto the stack. So while the stack is not empty, we print as we pop off the stack. And what does this print? What will this code print? This code will print Robert, 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 Robert. What happened to John, Sam, and Sally? They're gone. Why is that? Why does this happen? The reason why this happens is there's a single person instance. What we really wanted to do was to put 4 person instances on the stack. We wanted to push 4 people onto the stack. We pushed a single person on the stack, and we changed his name or her name every time. So taking a look again with the sketchpad for just a moment, what we have is person P equals new person. So this allocates on the stack a variable P, and then on the heap we have the actual person instance. So over here's our actual person, and here we have an address, and let's call this A for simplicity. Now we have an array of strings which are people's names. So we have the first one, p.setName John. So we have John here. Now we push this onto our stack. So this stack is the system stack. So we have our own data structure stack in our program here. And we will call this our stack. So it's a data structure stack, not the system stack. And we call stack.push P. Okay? So we put P on the stack. Now, we have push P, but what's in P? What is in P? The contents of P is A. So we haven't pushed a person on the stack, rather we have pushed A. That is the address of this object on the heap whose name is John. Now we loop back around and we have p.setName Sam. Okay, so we've set the name of this single person instance to Sam. And now we push it on the stack. And again, we push P on the stack, but the contents of P is A. Looping back around, we have p.setName to Sally. And then we have p.push, push P on the stack, and of course the contents of P is A. Looping back around, the final time we have p.setName Robert. So we set the name here to Robert. Then we push P on the stack, and of course the contents of P are A. So we push A on the stack. So contents of stack now are A. We thought we had 4 people, but we don't. We have one person whose name we have continued to change. So now when we pop off the stack and print, what do we print? We print Robert, 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 Robert. We don't have 4 objects, we have only 1. So as you can see here, we've only created one person. Person P equal new person, the first line here, and that's it. Another common error. We have a container that holds some object. So we create some item and set the description to ABC. And we need to put that in the container, of course. Item 1 equal new item. But we need to store that in the container, and I see that I'm missing that line, so we want to add that. C.add or insert 1. So when we get the description for this thing, we pull it out of the container and we assign it to 2. Then we change the description. So what happens here? Does one description change to DEF? Yes, it does. So again, I want to look at what's going on here. We have this container class. So it holds objects. We haven't specified the exact details of what they are. We create a new item. So when we create the new item, of course, the item is the first part of the actual instance. On the heap, because it's an object, is the actual item. And the address, the very first byte of this item, is what is stored here. So this is the item 1. Now we create another item variable, and this one is 2. But we don't have item 2 equals new item. What we have is item 2 is equal to 1. Therefore this becomes A. We have 2 objects that point to the same instance. So if we have 2.setDescription and change it, it is changed. It's just the one item. So with the first object, when we declared this, we have ABC. Then we use 2, and we have 2.setDescription DEF. Go to A and change the description to DEF. So again, we don't have 2 items. We have the variables 1 and 2, but both of them are references that point to the single item that exists on the stack. Another common error. So we have a swap function here. We have int A, int B, and we're just swapping those 2 values. Whatever A contains, we're giving it the value B, and vice versa. So if we call this swap function, what does the program print? int x equal 2, y equals 4. We swap x and y, then we print x and y, and we get x equals 2, y equals 4, and nothing has changed. Why not? What's going on? So, on the system stack, we have allocated x and y. X and y are created when we entered the method. X and y. X has the value 2. Y has the value 4. So at this point, this is in the main method. Now we call swap. And when we call swap, we push x and y onto the stack. So these are known as A and B within the swap. A and B, we have 2 and 4. We have pushed y and x onto the stack. We call the swap method, and in fact they do swap. They do swap as expected. A and B get swapped. So we now have 4 and 2. Then, of course, we return from the swap subroutine, and all of this gets popped off the stack and is now garbage. And what happened to the original x and y? These are unchanged and unmodified in any way. Therefore, I hope you're able to see x and y are unchanged by this function. It essentially does nothing, because what it does is it swaps copies of x and y that are on the system stack. Here we have another version of swap, but this time it is with integer A, integer B. So this time we have actual objects rather than value parameters. In this case, we want to look at what's going on, because these actually will swap. So again, we have our x and our y. And this is our main method. We then call swap. So when we call swap, we have the variables or the parameters A and B. But what's different with reference parameters, reference variables, is it's an address. Well, this too has an address. I don't know what it is. Let's make something up. 3B 4C 2110, and then this one would be 2114. So here we have for A, OX 3B 4C 2110. Here we have OX 3B 4C 2114. So now, when we have the swap, we have temp equals A equals B, B equals temp. We actually go to the addresses and change the values there. So the swap, by dereferencing these addresses, that is, it says go to A and read the value you find at that address. So now what we're actually swapping is not this field with the one below it. These aren't swapped. Rather, we go to these addresses and do the swap. We now have 4 and 2. So they have now actually swapped by using these addresses. Here we have swap xy, and they're not the same type. That is, the prototype of our function is integer A, capital I, integer B, capital I, and we're passing in instances of variables int x, int y. Java features what is called auto boxing, and so it will automatically convert between the two types for you, so you need not do anything special in order to make this happen. That is, In the calling program, you don't have to say integer x equals new integer 2, integer y equals new integer 4. Rather, int x equals 2, y equals 4, and then the conversion happens by the JVM. Just a quick recap, this won't work. Why won't this work? Linked list, list, list.insert. Remember that with object variables, there are two distinct pieces. Here you have only one piece. List is allocated on the stack because it's in a method. It's in main. So list is allocated on the stack, but list is a variable that will hold an address, and it's initialized to null. Only when you say list equals new linked list does it really exist. Until then it does not, and the dot operator in the list dot insert will cause a null pointer exception to occur. This is an error that's so common in student programs it merits special attention, so I want to call your attention to it here. Let's look at this. We have a stack class that we're building, and in this stack class we're going to use a linked list that we already have in order to make our stack. Look at the constructor. We have linked list equals new linked list, current size equals 0, looks fine, and then we have a push method, but I want you to note that the very first time you call this push method you're going to crash. You're going to crash with the null pointer exception. Can you see why you're going to crash with a null pointer exception? So again, I want to flip to the sketch pad and I want to look at what's going on here. Alright, so we have the stack here. We enter the stack with main. And then we have a variable that we declared. And this is our linked list list. And of course it's initialized to null as objects are until we use the keyword new to create them. Now we have the constructor. And so we're entering a method here. So this is main. And then we have the constructor. And in the constructor we have linked list list. Well, we have two names that are just the same, but it doesn't matter. The scope is different. This is, of course, the constructor. And here we have list equals new linked list. So over on the heap, we allocate space for our new linked list. And we will make the assumption that the starting address of this is A, so this is returned in. And the address here is A. So we have our new linked list created, ready to go. Then the constructor comes to an end, and so all of this is popped off the stack. We're back in main. And what is the value of list? Does it point to the linked list over here? No, it certainly does not. It does not. What is the problem and why did this happen? So why did this happen? Why would we get a null pointer exception? Because in the constructor we have declared a new linked list variable named list and created it, but that new variable ceases to exist once it goes out of scope. So the class level linked list list was never created at all. It was set to null at the beginning and it remains null, so when you call the push method and you say list.add first, you get an immediate null pointer exception because list is null. It was never allocated. What's the solution? to eliminate the declaration with the class name. That is, you do not want to say linked list list equals new linked list. You just want to say list equals new linked list. You don't want to allocate a new variable there. And if you say list equals new linked list, then it will be the class level variable that gets declared. The last example I want to look at, this is linked list code, which you'll be working on shortly. And it's not important exactly what's going on with this code. Rather, I want you to look at this, and if you can see, if you can identify where a null pointer exception will occur. So this code will crash sometimes, but not others. What's wrong with it? And the problem is the dot operators. When you get a null pointer exception, you should always think, where is this? Where are the dot operators that cause this? So we have a linked list here, and current is set equal to the head. But more importantly, we have current dot data. If current is null, then we have null dot data, and therefore we will have a null pointer exception and crash. So what you always want to look for with null pointer exceptions is where's the dot operator, the dereference, that is causing this to occur. Null pointer exceptions happen when you try to access either a method or a variable on an object that's null. And you do this with a dot operator. So this is what you always want to look to when you have null pointer exceptions, to see if you can identify the problem. So this concludes our lecture, and moving forward from here we want to look at generic programming and then on to linked lists.